Prove that if a statement can be proved by strong mathematical induction, then it can be proved by ordinary mathematical induction. To do this, let P of n be a property that is defined for each integer n, and suppose the following two statements are true. P of a plus 1, P of a plus 2, all the way up to P of b. Those are the base cases of strong mathematical induction. And we also get for free that for any integer k greater than or equal to b, if P of I is true for each integer I from a through k, then P of k plus 1 is true. So that's the inductive step of the strong mathematical induction. So we get those two properties for free. The principle of strong mathematical induction would allow us to conclude immediately that P of n is true for every integer n greater than or equal to a. Can we reach the same conclusion using the principle of ordinary mathematical induction? The answer is yes. To see this, let Q of n be the property that P of j is true for each integer j with a is less than or equal to j, which is less than or equal to n. Then use ordinary mathematical induction to show that Q of n is true for every integer n greater than or equal to b, which is that we need to prove the base case, and we need to prove that for each integer k greater than or equal to b, if Q of k is true, then Q of k plus 1 is true. This seems very counterintuitive. This is a very important problem because most of us think that like strong mathematical induction is required for certain proofs. But in reality, we can actually use mathematical induction, normal mathematical induction, every single time. We just have to be careful with how we define our predicate. In this case, they're literally giving us the predicate. The authors of the textbook are telling us what the predicate Q of n is that we need to prove. So let's prove both of these statements, starting with Q of b, which is our base case. So we have to ask the question, why is Q of b true? Why would Q of b be true? Well, let's identify what Q of b even is. Now, according to the definition of Q of n, Q of b is just this property here where we replace n with b. So Q of b is the property that P of j is true for each integer j with a less than or equal to j, which is less than or equal to b. Now, why would this be true? Why is P of j true for each integer j with a less than or equal to j less than or equal to b? Well, that's because we get to assume that P of a is true and P of a plus 1 is true, all the way up to P of b. So this is true by assumption number 1 up here, that P of a is true and that P of a plus 1 is true. We get this for free. So that proves our base case. We've proven that Q of b is true. Now let's figure out why the second part is true. For each integer k greater than or equal to b, if Q of k is true, then Q of k plus 1 is true. Why would that be the case? Well, we're going to assume that k is some arbitrary fixed integer greater than or equal to b, and we're going to assume that Q of k is true. So Q of k is the statement that P of j is true for each integer j with a less than or equal to j less than or equal to k. Now the second property tells us that if P of I is true for each integer I from a through k, that's what we have here. We have an integer j that is bounded between a and k. Then according to the second assumption here, then that means that P of k plus 1 is true. So by assumption number 2, this means that P of k plus 1 is true. But this isn't exactly what we wanted. We're almost there. We want to show that Q of k plus 1 is true. That's the goal of this inductive step. But now we have that Q of k is true, which means that P of I is true for each integer j between a and k, and we have P of k plus 1 is true. So this means in particular that P of j is true for each integer j with a less than or equal to j less than or equal to k plus 1. We have k plus 1 as well because we know that P of k plus 1 is true. We proved that using assumption number 2. But this is the very definition of Q of k plus 1. So what we just showed is actually that Q of k plus 1 is true. And so now we've shown that for each integer k greater than or equal to b, if Q of k is true, then Q of k plus 1 is true. So we've proven ordinary mathematical induction using strong mathematical induction. This is a great exercise. Thanks, everyone, and I'll see you in the next video.